Hey everyone, so we've seen the statement of the mean value theorem and a little bit of intuition for what it's saying. What I want to do right now is give you a proof of the mean value theorem using Rolle's theorem. So as a reminder, Rolle's theorem says if you've got a function that's continuous on a closed interval from a to b, that's differentiable on the open interval, and if it's also true that the y values of that function are equal at the endpoints, then it's going to be true that there must exist some point c in the middle with f prime at the point c equal to 0. So how can we use that to prove the mean value theorem? I've got a diagram here kind of set up to give you the strategy. Say we've got a graph of our function f of x, and this function f of x is assumed to be continuous from a to b and differentiable in the open interval from a to b. I've drawn for you the secant line from a f of a to b f of b. I've called that secant line y. And it has a formula, and we could figure it out, but that's not necessary for this proof. All that's necessary for this proof is to know that the slope of the secant line, in other words, the derivative, is equal to f of b minus f of a, everything divided by b minus a. So that's the derivative of a line, of course, is its slope, and that we know is the slope of a secant line. So how can I use Rolle's theorem to prove the mean value theorem? Here's the strategy. So I want to define a new function called g of x, and g of x is going to give me essentially this length. It's going to give me the signed distance from f of x to y. I'll write down the formula for it. Let's define g of x to be equal to f of x minus y. And the reason I called it signed distance is because if f is bigger than y, it's actually the distance. If f is smaller than y, it's the negative of the distance. And when you look at this, you can say, okay, does this satisfy the conditions of Rolle's theorem? I want to use Rolle's theorem on the function g. And since f is differentiable and continuous, and the tangent line, the linear function, is certainly continuous and differentiable, so their difference is still continuous and differentiable. That's fine. What about showing that g of a equals g of b? Well, you can see it from the picture. Since we know that's the signed distance, g of a, that's 0, g of b, that's 0. The distance between them is 0 when they intersect. And you can see that analytically here from the fact that the secant line has to be equal to the value of the function at precisely x equals a, x equals b. So this tells me now, Rolle's theorem tells me that there must exist a point c that's bigger than a and less than b with this function g prime at the point c equals to 0. And now I claim to you that that finishes the proof, and let's see why. Because if I calculate g prime of x, that's going to be nothing but f prime of x minus y prime, but y prime is equal to f of b minus f of a over b minus a, right? And so when I say that g prime at the point c equals 0, I can just plug that into this equation. So I plug in c, and it's supposed to be equal to 0. Let me come down here and fill that in. So 0 is now equal to g prime at c, which is now equal to f prime at c minus that slope. And now you see what's happening for sure, because in order to get the conclusion of the mean value theorem, knowing that 0 is equal to f prime of c minus the slope of the secant line, I need only bring this over to the right-hand side, and then I get the exact statement of the mean value theorem, that there exists a point c such that the derivative is equal to the slope of the secant line. So that's a really cool application of Rolle's theorem, a nice step-by-step process getting us really from the definition of derivative all the way to the mean value theorem.